morning, all of you, to the joint workshop of the Spectrum project and also of the IEA Solar Heating and Cooling TCP Task 72. So I welcome you, both the ones that are here in person, and also to our online participants that are looking through that camera over there. And so we have for today a program dedicated to, or mostly focused on, materials for photoreactor applications. And we will start by a short introduction to Task 72 project that will be followed up by a presentation from the Spectrum project on sacrificial agents for fuels and chemical production. So without further delay, I would like to ask Bettina Muster.
Thanks, Charles. Welcome everyone, especially also a very warm welcome to the new or not Task 72 participants who don't know the Task 72. So nice to be able to introduce our work to you. And who knows, maybe we see the one or the other face in one of our future meetings. Many thanks, Charles, for organizing such a, let's say, public workshop as well. I know this is an effort, an additional effort, but this is really, really well appreciated also from the solar heating and cooling TCP, that we actually spread the word, spread our work, and of course highlight also important projects that are connected to the task like the Spectrum project. Task 72 has kicked off in November 24, and we will work until October 28. The title Solar Photoreactors for the production of fuels and chemicals. So we would like to address technology that use solar radiation in advanced solar collector reactor configurations to run photo processes, be that photothermal, photocatalytic, or photoelectrochemicals. Now, why did we have this vision to do this? On the one hand, the vision is really to produce new collector reactors and integrate inside such photo processes. No matter whether we would like to produce fuels, we would like to produce hydrogen, we might want to produce methanol or ethylene or ammonia or other chemicals. But why has this been triggered? We've been seeing a large need in development of such reactors on two sides. On the one hand, from the photocatalyst research side, or photoactive material research side, which has been there for decades, and it's a large research field. However, a lot of the research was dedicated to the lab. And on the other hand, we see it from the solar industry side, where solar thermal collectors have actually on the market seen rather hard years in the past. I would say in the past decade. And here also the development need actually towards new products, new visions, etc. So in that way, we saw this urgent need to link actually the photoelectrochemical and photocatalytic expertise with the solar expertise, because if we want to bring such reactions outside to real sunlight, we'll face new challenges. And on the one hand, the solar industry knows, at least to some extent, how to deal with those challenges. There will be new challenges coming with the new reactors, but to some extent. And these challenges are how to focus our photons to the spots we want, where we would like actually to have the reaction happen. What is the best materials, what transmittance, which flow behavior we want to in the different versions of catalysts that are available, powder, coated, etc. And what is also the effect of heat reaction kinetics, or how can we deal with thermal management? These are all questions that become very important. So we thought, okay, well, we need to initiate a task on this. So what is the task? In the solar heating and cooling TCP, and as in other TCPs of the International Energy Agency, a task is basically a collaborative project internationally, over many experts. Now, the IEA and the TCPs, they don't fund the tasks money-wise. In the SHC TCP, we don't receive money for that, but this task aims to form an expert network. This is a crucial importance. To be able in this network to exchange results, not having to have the best results like in a conference, but you can really come here with intermediate results, with methods, approaches that we use. We share them, so everyone comes with his own projects, brings in his expertise, get expert feedback, also in open discussions, support. And what we would like to aim for is put our individual results and knowledge together to synergistic results. And this could be a position paper, could be a guideline, could be definition of metrics that we want to have for comparative assessment. Why are this? The task wants to make an impact to research, but also to industry. And you, on the other hand, get inspiration for your own work in such a network, and of course, it can fuel further collaborative projects. And this is very well in line with the solar heating and cooling strategic objectives, which are analyze, research, connect, and communicate. So these are, let's say, the core pillars, what we would also like to reach in the task. Now, the task 72 was then had a one-year definition phase, and we structured it into 3 subtasks. So we have 3 subtasks. Subtask A on materials and component development, led by Victor de la Peña from IEA Energy, who's here with us. Then subtask B on reactor design, led by Sarah from ETEC, of my group, and subtask C on system integration, led by Sixto Malato from CMA. Now, in each of these subtasks, we formulated core activities that we would like to work on. So work on basically means discuss, bring together results on these topics and see what can we do synergistically with them and exchange on that areas. In subtask A on the materials, it's material design and selection, synthesis and fabrication. It's characterization, standardization, and testing. And you will see these words coming up now in all the different subtasks. And optimization and scaling. So how can we bring methods on how to prepare electrodes, for example, to larger scales? In subtask B, the aim is to, on the one hand, review existing photoreactor designs, try to analyze and assess different photoreactor processes. So what is happening really inside the photoreactor, which steps of the reaction happen, and how can we improve them? Also collaboratively define key performance indicators. So here you see again coming into a standardized framework for assessment. And finally, to come up with design strategies for solar photoreactors for different processes that we would like to perform. And here I can bring you one example of the collaborative work that we just performed recently. So via the task network, we collaborate now with the university in Germany. This is not, let's say, a special funded project, but basically it was the idea they work on a reactor. We do solar assessment and reflector design. So they sent their reactor over, we designed the reflector, and we are now measuring it at our roof. Yeah, and this is, let's say, happened or was induced via the task. And I think such collaborations can be nicely boosted by network. And in subtask C on the system integration, the relevant topics are piping and instrumentation diagrams. So here it's very nice to get from different projects, different flow schemes, different piping and instrumentation diagrams, but we can also learn from each other. Standardized procedures again for testing. So see, this is coming up again and again. Life cycle assessment is an important pillar to really get the environmental, economic, and social views of the technologies but also their applications. Standardization of solar conversion for a full system evaluation, and in general also this would be a later stage. Could we come up with potential studies for photofuel production? Now, we have focused on few deliverables per subtask. So we can actually try to focus on a few documents that we would like to achieve. And what we came across then, or when in the discussion of the subtask definition, we can actually see that we would actually like to work on very similar aspects on the different levels in the materials, in the reactors, and the systems, and they of course also interfere with each other. And the one hand, these are always design strategies, yeah. So how to design materials, how to design the reactors, and how to design the systems, or how can the flow scheme look like. And on the other hand, standardized protocols on the one hand for the material synthesis, for their characterization, but also for testing then on the one hand the reactors themselves, but also the full systems in relation to sub-16. Now, as this came now a lot when you need to work on key performance indicators, make comparative assessment, I give you a glimpse of our current work. And this was actually a discussion that we had yesterday morning. We want to foster the definition on which key performance indicators are really important for the community, on the one hand in research, but also when we communicate to the outside world. And now we did a survey internally in our network, and it was filled by 29 experts. And one of the questions we ask is, which performance metric do you currently report on? And we just see there are many, and it doesn't mean that there are too many now. But all of them have a different aspect, are differently important, depending on what you want to analyze. Yeah? On the other hand, the second question was, which single performance metric do you consider most important? And then also the, let's say, views maybe differ a bit. Some higher priorities, but actually all are relevant. Yeah, you wouldn't say some have been by no one, and then there are still also others which are probably not here on the list. So these are just now 2 questions out of a much larger survey that we did, but it should just show this or underline really that also this importance is seen in our expert network to work on that. And we initiated this work yesterday, where we first had the objective to really define metrics for the material, for the reactor, for the system level, and then work further on such protocols. And just to show you how this can be the living work, so this is a living slide from yesterday's outcome, we then said, no, we'll do it differently. Yeah, let's focus on different scales and try to work on key performance indicators which are relevant for different target groups. Yeah? And this is now a current work we are performing, where we will collect information to a large table from all participants and then have task forces on each other. For a task, it's of course also important to communicate not only internally, yeah, or work internally like we show now with these metrics, but also communicate then to other TCPs or to other, let's say, expert networks that are available. And one example of this is we have been invited to the IEA Hydrogen workshop in Paris on solar to X technology. And this was co-organized by the Hydrogen TCP, by the Mission Innovation Solar to X community and the Synergy Network. And this just means also such a work on key performance indicators, but also in other topics that there is also an exchange with other networks. The SHC TCP, of course, also can help you in promoting your work, yeah, with newsletters, etc. So if you're part of the network, this is also something which we can use. And there has been, for example, a news article on Subtask A by Victor. In our network, we have now over 40 active experts, and we meet every half a year. Of course, not everyone can come to every meeting, but we have been in the past always 25 people or so online and in physical at the meetings from 11 different countries. So Austria, Germany, Italy, Portugal, Spain, Australia, Canada, France, Poland, Netherlands, and very recently South Africa. Yeah, so some impressions, and in these among these experts we have over 50 different running projects on the topic. Yeah, so this just shows how much let's say wealth of information comes together. What are such project examples? Actually, there very wide. So of an idea what different projects could work on. But if we start it's for the production of different user chemicals, most of them currently for hydrogen syngas, or methanol, ethanol, and ethylene, and ammonia. So these are the core products of those running projects. Not saying that's limited to them. Yeah, what are the next collective activities in our subclass? On the one hand, as said, we work on key performance indicators. In subclass A, we are working on a knowledge document on photoactive catalysts. In subclass B, currently working on templates to collect various solar photoreactors design. And in subclass C, putting together PNI schemes of different plants, and also this work on sacrificial aid. You actually see a very nice presentation today. Yeah, the next smart meetings are coming up in Austria and in Germany next year, and yeah, join us. We not only work, we also sometimes get perfect tours to different European cities. And yeah, I can recommend shower and living all the time.
Thank you very much, Bettina, for the presentation. So next in our program is a short presentation about the Spectrum project, which will be delivered by me. The Spectrum project, as the name. Yeah, okay. The Spectrum project, as the name itself, it's an European project from the Horizon Europe that started 1 year ago, basically. So it started in 2024. So we have run through the first year of the project. And these projects, so what does Spectrum mean? Spectrum means solar polygeneration collector for combined heat power, hydrogen fuel, and wastewater treatment. So what we do, as some of our partners, at least one partner says, it's the Frankenstein collector, a collector to do it all, let's say, or if you better like Lord of the Rings and things like that, one collector to do it all. And what is basically a development of two collector designs. One collector is a flat plate collector for low temperatures, and the other one is a concentrating collector for higher temperatures, where we are trying to harness in a better way the solar radiation and try to maximize its use into the production of different useful energy vectors. And at the same time, doing wastewater treatment is a kind of a bonus that we get from the technology that we are trying to develop. So why the interest in developing these collectors? So from the website, and as most of you are well aware, the industrial production processes account for a considerable share of the energy consumption and also the overall pollution in the world and also in the European Union, due to the emissions of greenhouse gases, pollutants, the discharge of wastewater, and also generation of waste. And at EU level, the industrial sector is responsible for roughly 26% of the final energy consumption. And in terms of worldwide, this is 33% for the total energy consumption. And it is responsible at the EU level for 24% of greenhouse gases emissions and 54% of the water that is consumed, and therefore of wastewater being discharged into the treatment systems. Yes, I know. Don't worry. This is it's a long introduction. I will short it up. Don't worry. So my presentation. This exactly. This is why the Spectrum project aims to create these innovative solar technologies targeting the industrial sector and industrial applications. And what we are doing is conceiving, developing, and prototyping, and also testing at lab scale these two prototypes of these solar collectors that aim to fully harness the solar spectrum, okay, converting it into these three energy vectors: solar heat, solar electricity, and hydrogen, while performing the industrial wastewater treatment. It's a little bit more tricky and difficult than it seems, particularly this aspect of maximizing the use of the solar spectrum. Okay, this is a critical aspect that that we have. Oh, and now I see that this now it's not passing. So now I have okay. So why the hybrid approach? Okay, so what I have here is the solar spectrum for a typical clear sky day. So this is the AM 1.5 spectrum. So this means that this corresponds to the solar position roughly at 42 degrees of elevation, and for a 1000 watts per square meter irradiance in a surface with 37 degrees of inclination, right? And so we have the total solar spectrum, which is the top of these plots here. And for typical PV models that have an electric efficiency roughly between 15 to 20%, if we consider silicon, the average silicon cells, some of them can achieve a little bit more, 23%. What happens is that we only get this blue area here of energy out of all of these solar spectrum, right? And the rest, that is this yellow and this light gray area, is converted into heat. So about 65 to 70% of the solar radiation in a PV panel is converted to heat. In a thermal collector, we can convert a little bit more of the solar radiation, but usually we can convert into useful energy about 50, 60% of what we have here. So therefore, there is this idea of developing hybrid solar collectors in order to PV collectors that are most well known and are currently at the commercial stage and also being a focus of intense developments at this moment, where what we aim to do is to basically merge the PV with the solar thermal, right? So, and these collectors are designed to convert part of the spectrum, this blue area, into electricity, and then harness a part of the heat that is generated and transfer it to useful thermal, heat transfer fluid. So typically in these collectors, we can go up to 60% of thermal efficiency. So global efficiency is around, these are ambient temperatures, so it's for very specific applications. And we can have here combined efficiencies that can go up to 75%. So these would be the blue and the yellow area that we have here. So within I see now that this is not exactly the same point as I have in my computer, sorry. So the blue and the yellow, yeah. In spectrum, we are trying to improve on this, on this PVT concept by adding an H, so a PVTH collector. And we are doing that using photocatalytic reactions that will harness a part of radiation that is here on these left side of the spectrum, right? So we are trying to harness UV light and trying also to develop active photocatalysts that can go a little bit to the visible. Not much actually, because then you have to balance all of these three let's say conversion units, the photovoltaic, the thermal, and the photocatalytic. And if you want to achieve some given temperatures, you need to have a balance. Okay, it's not a given that you can achieve all of the temperatures if you use too much energy for the PV or for the hydrogen production. Okay, so this is a little bit about the why, let's say, a little bit of motivation for this. So the Spectrum project in a short glance, as I was mentioning, and again, I'm not passing here this, so sorry. Yeah, okay. So this is an Horizon Europe program, project, as I said, started last year and it will end in March 2028. It has 10 partners from different countries. So starting from Portugal, LNEG, ourselves, the project coordinators, and also the technical university. Well, it was, now it's the University of Lisbon, but it is the Technical Institute or High Institute of Lisbon, ISE. Then moving to Spain, we have CIEMAT, the Plataforma Solar de Almeria. In Italy, we have Unibu also as a partner. And we have Fraunhofer is from Germany. Belgian Volt, that is a control, it's a company specialized in control systems. The Imperial College of London, so again, also an RTO. And from Sweden, we have one university, the University of Gävle, and two companies. That is MG Sustainable and Solarus Renewable. So in this case, Solarus Renewable is a developer of a type of PVT solar collector. And one of the things that we are doing is adapting this PVT collector to produce hydrogen as well. Okay, so a little bit further on this part. What is the aim of this project? Is, as I mentioned, to develop, validate, and test these concentrating solar hybrid concentrating solar collectors, and targeting three different challenges. One is the decarbonization of the industrial sector. That is currently one of the major hurdles to achieve carbon neutrality targets that have been established by the European Union's long-term strategies, so by the climate neutrality in 2050, and also to do this, the great deployment of heating, of renewable heating technologies is critical, because roughly 70% in Europe, 75% of the energy consuming industry is heat. So therefore, renewable heat is crucial for this achievement of carbon neutrality. However, up to now, very modest improvements have been made, and the deployment of renewable heat or renewable-based solution has been quite slow in the industrial sector. So we take on this opportunity to tackle this challenge by developing and demonstrating the technological, environmental, social, and economic feasibility of these new collectors and of this, let's say, free vector production collector. And this is here actually something that connects quite well with the discussions that we had yesterday. So we are doing LCA analysis, so prospective LCA analysis for our collectors that will start actually now in this second year of the project, and also doing some social analysis of the acceptance of these type of technologies by industry players and also by the general community. Another aspect is that if you think of industries and if you think of our cities as well, but here thinking more about industries, many times they already have existing buildings, and the availability, the space availability to implement renewable technologies can be scarce, or there can be space for different technologies. So I think also one challenge is to maximize the local generation of renewable energy at industrial sites. And this is also something that we are trying to tackle by delivering a new concept of the solar collector with optimized use of the solar spectrum that can generate the heat, electricity, and fuel, that in this case hydrogen, in industrial sites or other artificialized surfaces. And finally, there is the challenge related with the reutilization, valorization of wastewater, treatment of wastewater and sludges, and that are required to achieve the Sustainable Development Goals, and also to alleviate adverse environmental impacts of wastewater in the environment. And here we are boosting the sustainability of the industrial wastewater treatment. So we are not developing a collector that will treat all of the wastewater. So we are thinking of treating some waste streams before they are mixed together, or treat some specific wastewaters. And so if we do this in this way, we can alleviate the treatments, the specific treatments that the industrial facilities need to have. And so the goal is to try to enable an easier and cheaper permit for the pre-treated industrial wastewater discharge on conventional urban wastewater treatment plants. So this is, let's say, the concept that drove us here. Okay, so now about our organization. So we have divided the project in 3 stages or 3 phases. One phase dealing with the technology developments, and that has 2 work packages. A second phase dealing with the prototype design, construction, and testing. And the third phase dealing with the techno-economic, environmental, and sustainability. That is, let's say, at the end of the project, but not only. It's moving through with the project. So in the first phase, what we are doing is we are optimizing photocatalysts for some wastewater streams. So the next presentation will deal with this, at least with the identification of the wastewaters, the suitability of these wastewaters. And we have been working not only on identifying the suitable wastewaters, but also on developing new photocatalysts targeting these wastewaters, and also the development of these 2 collector concepts. That is a collector that we call it spectrum low temperature, LE, that is the one, let's say, targeting a temperature of maximum temperature of 100 degrees of operation, and the spectrum high temperature that is targeting an operating temperature of 200 degrees C. And of course, with these designs, we will build the prototypes, we will design for manufacturing, we'll build them, we will test them, and from performance data and the construction data, also starting from the development stage, we will give these inputs to the techno-economic, environmental, and social sustainability. So basically, this is the structure that we have, the different work packages. And so one dealing with the optimization of the photocatalytic process of wastewater treatment and the hydrogen generation. Another one dealing with the polygenerating collector design and optimization. All of these will provide information for the prototype development testing, and basically all of these 3 will provide information to a work package that is a prospective work package dealing with the integration of these technologies in industrial processes, how we can do it. So we are in a very low TRL. We started in TRL 1 and we are going to move to TRL 4, but we're already thinking about how we can afterwards move to higher TRLs and really integrate these collectors, if they work, in the industry. And of course, all of them provide information for the sustainability evaluation. And yeah, I will just end up by saying that we are also developing research and development and innovation hub. So the goal here is to engage and facilitate a collaborative space between hybrid solar collector focus groups at European and international level, trying to address research and development topics for hybrid solar collectors, and just building upon the experience of participating groups. And we are now having internal discussions on how to launch this. We have done this in other projects for PVT technologies. We created, in this case, together with MG Sustainable, that is the PVT4EU coordinator, an initiative targeting students, early stage researchers, that is called PVT Nexus. And it's a kind of an interesting network. And here maybe we will do something similar also for this area. And I think it's very interesting to push for the synergies among Task 72 and also 73 as well, and other initiatives that we have. We will start to have these discussions now also in this second year. Yeah, so thank you very much for your attention, and if you have any questions, you can do it now, or you can also write an email or check our website. Okay, so now we will have the third presentation, and yes, it's easy, and the final one before the. So the final presentation before the coffee break, that is a presentation by Carla Pinheiro, professor at the High Technical Institute of University of Lisbon. I never know how to say IST in English, but
Technical Institute.
So I thought it's High Technical Institute, something like this. So Carla is a professor at the Chemical Engineering Department, and so she will present us today on the spectrum development dealing with the selection of industrial wastewaters.
So I will talk a little bit and give you some highlights of some work that we have done in collaboration, our core teams, ISPIB, which is my university, LNEG, and the team of Unibo and CMAC Spain. So Marcos, Sisto, Alexandre Esteves, Maria João, Ana Lana, and Guilherme Pedro. So this is part of one of the work packages of the project Spectrum, and I will give you only some highlights of what has been done, and also which is included in a deliverable, which is public and is accessible, and you can have access through our Spectrum webpage.
The other one.
Sorry.
Too many mouse.
Too many mouse. Yeah.
This one.
So as João told you, Spectrum project objectives are design, develop, prototype, and test large-scale solar collectors that effectively utilize the entire solar spectrum to co-generate heat, electricity, and hydrogen. You have here the website for our project, and well, I highlighted hydrogen because it's about hydrogen that I will present you this first developed work. So, as we all know, green hydrogen is one of the solutions for the decarbonization pathway. So that's what we are looking for also here in our project. Also, our motivation, and I will show you some, a picture that I took from Hydrogen Roadmap Europe, where we can see that with an ambitious and optimistic, projection or prediction, hydrogen could provide up to 24% of total energy demand up to, around 2050, as you have here. And as we can see, although in this document, in this report roadmap, final energy demand is decreasing a little bit, the global, which I think that today it is not such a very true reality. Regarding hydrogen, we can see that it will increase, of course. So we are expecting to increase the need for hydrogen to be used in several sectors, such as power generation, transportation, heating, industry, energy, and also doing industry. So regarding industrial applications, we have the production of ammonia, which consumes a huge amount of hydrogen. We have also methanol, the refining industry, and some other sectors, other industries. So when we talk about hydrogen demand in industries, what are available pathways for hydrogen in industry? So we have different applications of hydrogen as feedstock, as a fuel, and as hydrogen for self. And we see and we know that the application of hydrogen is increasing in all these sectors. So we have several competing alternatives, and depending on the industrial sectors. So we have hydrogen from steam methane reform, which is nowadays the most of the hydrogen that is produced from fossil fuel. Now we are increasing hydrogen from electrolysis, and so we have different types of applications. And you can see in bold some industrial sectors that have availability of wastewaters and that can match perfectly and very well with our project. So where hydrogen can be used for wastewater treatment. So they produce wastewaters, industrial wastewaters that can be interesting from our perspective. So just to give you an idea of the main benefits of the production of hydrogen via solar photocatalysis of wastewaters, this is what I'm just going to talk a little bit. So we have this dual environmental benefit. Also, João also told you a little bit about this. So we have enhanced sustainability with simultaneous wastewater treatment, pollution abatement and renewable energy generation, circular economy approach. We transform organic pollutants into valuable energy rather than waste. Low-cost feedstock uses industrial or municipal effluents instead of pure water. This is our goal. Reduce carbon footprint because we want to rely on solar energy as the driving force and no external energy required. Decentralized energy production, so with on-site, and this is very important, on-site small-scale hydrogen generation integrated with wastewater treatment plants, and also the scalability and adaptability, which is applicable to diverse wastewater types, agro-industrial, municipal, and also supports EU Green Deal goals, contributing to renewable energy targets and zero pollution objectives. Well, so the highlights of some results and some work developed that I will show you in this presentation was developed within the scope of one work package, which is has the title of optimization of the photocatalytic process of wastewater treatment and hydrogen generation. So the IFC partner focus at the beginning, our team at IFC was to select and characterize potential industrial wastewaters that I will see in my presentation as IWW for the photocatalytic process. So to combine the potential for pollutant degradation with the production of green hydrogen. So our initial objective is the selection of industrial wastewater for H2 generation. This is something that is not found in literature. If we look for, we don't find many works or many papers or many work developed using real industry wastewater. So our main goal in our project is, in fact, to show that it is possible to use and try to select what are the best options regarding these different types of wastewater, because as you can imagine, we have different sectors of industrial sectors, we have different types of industries, and we have a variability, a huge variability of types of wastewaters and of side streams with water that are not used later. So the work that has been developed within the scope of this first task, as I could say, this selection methodology was based on we developed a public report that you can find at the webpage of the project, which is entitled Guidelines on the Potential of Industrial Wastewaters as Sources of Sacrificial Agents for Photocatalytic H2 Production. You have here the table, the contents, and this is the report. So in this report, we have a set of guidelines on the industrial wastewater key characteristics that are best suited for the photocatalytic process, maximizing the hydrogen cogeneration field and their effect on the photocatalytic process. I can tell you that the photocatalytic process itself and the photocatalysts are being developed in the at LNEG by the LNEG team in this work package. So we have also made some literature review of the production of hydrogen using these real wastewaters and what are the target industries and practical information for the selection of the best type of water. So we came up with a kind of a flow chart with a sequential steps that we call decision tree on the selection of these potential industrial wastewaters. So I will give you only a short introduction regarding the photocatalytic water splitting process, because, well, this is also important so that we understand why are we and what happens. So the production of hydrogen can be achieved through a process that is already being studied, which is the water splitting process. In this water splitting process, we have water, we have a photocatalyst, and with solar energy, we obtain hydrogen. So the splitting with hydrogen and oxygen. So this reaction has several steps. We have first the absorption of sunlight and the generation of electron hole pairs. So what do I mean with these? So the photons will excite and will make the electrons of the catalyst generate or increase in energy. So we have an energy, high energy for these electrons. So these charges migrate to the catalyst surface, giving we have what we call a connection band, where the electrons migrate, and we have what we call this H plus, so the holes, positive holes, and where we call the valence band, which will oxidize the water from oxygen to form oxygen, and the positive charges of the hydrogen, the protons, will take advantage of these electrons generated at the connection band and will give as product hydrogen. So some example of photocatalysts that have been used for this process. So it's titanium dioxide, some metal sulfides, carbon nitrides, and several others. And usually they are doped with platinum, copper, iron, and some studies with carbon materials that improve the oxidation of the water at the valence band. Okay, so we talked about, I started talking about sacrificial agents. So what we are interested is to find these sacrificial agents, SA, in the wastewaters. And the photocatalytic hydrogen evolution can be enhanced by using sacrificial agents because one of the disadvantages or one of the problems of this water splitting is that it is a very low rate process and not very efficient, because the electrons can regenerate and can come to the holes, the positive holes. So this is not a very rate or very effective process. So several sacrificial agents can be added to the reaction system to act as electron donors to the catalyst that will improve the hydrogen evolution rate, which is HER. So since many organic pollutants found in domestic wastewaters or industrial waters are suitable candidates to act as sacrificial agents, photocatalytic hydrogen production, merge this solar energy harvesting with wastewater valorization. And we can address simultaneously the remediation of these pollutant organic compounds in wastewater and the regeneration of green hydrogen. You have here some examples of the types of compounds that can act as sacrificial agents, so improving the oxidation of water and them being themselves oxidized and low, and so improving the rate of oxidation at the valence band. And we have alcohol, saccharin, carboxylic acid, amine, and sulfite and sulfite, and different types of compounds that have already been tested that can be interesting and can be used to increase the efficiency of the production of the photocatalytic production of hydrogen at the catalyst. So some key characteristics for the solar photocatalytic hydrogen production. These are some of the topics and some of the important characteristics that we have included in this deliverable. So some important aspects are typical industrial wastewater characteristics and composition. As I was saying, we have a huge variability. The sacrificial agents for the wastewater splitting, the organic load parameters, light absorbing and scattering compounds also present in the wastewaters, inorganic ions, pH dependence, and dissolved oxygen. I will not talk about all these characteristics. I will only highlight, give you some highlights of them. Because regarding some of these characteristics, there is also some different conclusions or different results found in literature. So there's, for example, regarding pH dependence, because the influence depends very much on the type of sacrificial agent that is being used, and so there are not very so the conclusions and are not the same for all the types of sacrificial agents. As I was saying, only few published studies, we found only few studies regarding the use of industrial waters for this process of production. So regarding the typical industrial water composition, they vary widely in composition, characteristics, flow rates, temporal patterns, daily, seasonal, and annual, and we have across different sectors. So as a result, it is difficult to define a single set of representative characteristics for all types of industries effluents. We try to make a kind of systematic or to systematize the literature. So industrial wastewaters are commonly divided into those predominantly containing inorganic compounds and those primarily composed of organic compounds, and also it's related to pollutants concentration, because of course we have different concentrations that we can find depending on the chemical sector, and only sometimes we have few compounds, high concentrations, and in other types we have lots of compounds and low concentrations. Another important characteristic or key parameter are the sacrificial agents, as I was saying. So even though possible sacrificial agents are present, few studies have applied solar wastewater splitting directly to real wastewater samples, and many available studies use model wastewaters. In our project, we will use and we will test real wastewaters in this process. So examples of wastewater of industrial sectors and the key sacrificial agents, we have here some examples. For example, the rice processing industry, brewery, dairy, olive oil, wine, and the types of wastewater, some from effluents, some others. We have also wine from the wine industry, wine wastewater, and the types of key agents that we can find in these types of wastewaters. Regarding organic load parameters, the organic load poses a great deal in developing the photocatalytic process. because much of the organic load in the wastewater will be integrated into the various reactions, some of them as sacrificial agents, and will benefit the process. However, the variability of the organic load, both in terms of quantity and composition in these wastewaters, represents a challenge when we are selecting a suitable industrial wastewater. Several parameters that need to be studied concerning the organic load that we have to analyze. It's the BOD, COD, TDS, solid chemical oxygen demand, several parameters that are important. So the literature also presents various concentration ranges, for example, for the chemical oxygen demand, and the real industrial wastewater samples collected, they exhibit a broader range of this chemical oxygen demand concentration between 0 and 1,000 milligrams per liter, for example. So some studies in the literature have reported some cases where these parameters reach significantly higher values also. Also, an important parameter is the light absorbing and scattering of the compound due to the type of compound in the wastewater. The main relevant factor is the presence of suspended solids, colloidal particles, and overall turbidity. And suspended particles are generally larger than 1.2 micron and are often settleable, whereas colloid particles are small. So this will also affect, of course, the light absorbing of the wastewater. Surfactants are frequently present also in the wastewater due to their widespread use, for example, in cosmetic, pharma, dyes, textiles, and this leather tanning industry. And these substances may cause bubbles or foam that can catch the light. So this have been So regarding the potential industries and practical information, the selection for solar photocatalytic hydrogen production, also with simultaneous decontamination of these types of wastewaters, because some of the compounds, of course, will be treated, so will be changed, they will react. So should be based on four main factors: potential industries and types of streams, relevance in the wastewater parameters that I talked about, and pretreatment steps and logistical considerations. So there is all this practical information to be taken into account. Selection of industries and type of streams, since we want to see in our spectrum prototypes to produce heat and electricity alongside with hydrogen, the selective wastewater should come from an industry that can integrate and utilize also these energy outputs from the prototype. So this can be integrated, all these goals. So some factors to take into consideration, these are some, I told you that these are some highlights because this is from our deliverable, this report that has 45 pages, so a lot of information that can be found there. But we can utilize wastewater streams that lack treatment methods, that are costly to treat and are not treated or are not treated at all. They can be used here in this process. So preferably that the sample is not from the end process stream itself, but rather from a byproduct stream or a medium to small volume in the wastewater stream. So these are also interesting streams to be considered. The biodegradability is a critical issue, and also the relevant wastewater parameter and sacrificial agents, as I presented. So the selection of suitable streams inside one industry, in the processes in one industry, will be a key topic for higher concentration and purity of the sacrificial agent, and should contain compounds that are not easily recoverable, for example, for other purposes. So they can be used here and degraded here. So priority potentially given to industries typical of Mediterranean countries, of course, Portugal, Spain, Italy, and some others, such as olive transformation, wine production, textile industry, tanneries, paper, wastewater, paper, and all these type of industries. Of course, when we talk about wastewaters and all these different compositions and compounds that we find, sometimes we may have to make to pretreat. So we have to include some pretreatments on some industrial wastewaters so that they can be suitable for the use in this process of photocatalytic hydrogen generation, and depend greatly on the type of industrial wastewater and the source industry. So we can include typically population sedimentation to remove large and suspended solids. Of course, we cannot use in photocatalytic process with suspended solids, the water with suspended solids. This is physical processing. Filtration to remove smaller suspended solids to prevent light attenuation. Dilution to adjust organic load. Also, and pH adjustment if it is needed to neutralize strong acidic or alkaline streams using cost-effective agents. Sorry, the reference is here. Regarding the logistic and supply chain considerations, of course, we have other aspects to be considered, such as sample preservation conditions. Well, if we want to test, and in our project, we must have this in mind to have the sample preservation conditions either for transport or for storing. In the case of a priori testing of possible industrial water samples. For example, we can understand that alcohol that are very volatile or other possible sacrificial agents could evaporate, and other compounds can biodegrade if they are not preserved. Sacrificial agents should be compounds soluble in water, preferably, and availability of wastewater, including seasonality and daylight patterns, must also be considered, because if we think on olive oil, we see that it's not during the production is not during all the years, so this can have only seasonality. So flows produced, and if they match the photocatalytic treatment capacity and land area for solar exposure, so these are also logistical considerations. So industries need using hydrogen, the purity of hydrogen and flow, jointly with heat and electricity. And we come to I will now present after this analysis, after all these analyses that we have made, we come to these flow charts that I'm only showing you now. The first part, where we have steps and pathways to start talking with, for example, if we go to an industry, we have to follow all these steps. If we at the end, we want to say, well, this is possible, this is a suitable or not suitable sample to be used, or type of waste. So we have some questions, and we have this kind of flow chart. I will only show you this first in great detail. Does the industrial process have clean or wastewater? If yes, well, if no, unsuitable, of course. If yes, are the organic and inorganic compounds present in the industrial wastewater that can act as key sacrificial agents? For example, alcohols, all these types of sacrificial agents that we listed. So if yes, we go to another question. If no, it is not suitable, because we need these sacrificial agents so that this process can be effective. Then we have this other question: does industrial wastewater contain any catalyst, poisoning, or inhibiting compounds? Well, of course, if yes, we cannot use this type of wastewater, because the poisoning compounds will poison the catalyst. So are there suspended solids in the industrial wastewater? And we go down, and we have all these decision tree. Then we can have yes or no. If we have yes, if we have suspended solids, they should be subject to pretreatment. If they don't have, we have another question regarding liquidity, and so we come to, for example, if we follow this yellow pathway, we can come to the best industrial wastewater candidate. or to some results that are likely candidates subject to pretreatment or the subject to treatment and testing. So we have these kind of flow charts that can help us in this selection. This was the first part that I've shown you. And we have also selected, so I will only show, we have also a milestone with 5 real industrial wastewater sources that we selected as the most promising or as the most likely candidates. Well, in fact, we had 8 likely samples following that decision tree. So practical application, these are some results of the practical application of the real wastewaters that we collected for our project. So practical this decision tree, and the sequence of questions were organized in terms of relevance. We have on top, and we made these. So the first 2 questions are eliminatory, and then we come up with likely candidates, or well, these are the 8 that we found the most likely candidates. So we have a ranked short list of samples with the screening assessment. And these are some analytical parameters that we had to characterize for these 8 selected most promising candidates of wastewaters. So we have different types of parameters regarding the inhibitor for the catalyst, the catalyst poisoners, sacrificial agents, light scattering, and general parameters. So we have here all the parameters that we have analyzed for these samples. And well, we reduced these 8 to 4 most likely candidates, and from these 4, we have now 2 most likely candidates. We have another sample that arrived this week, so it's not included here. We will characterize it, and then maybe we will have good result. We expect to have good result because we expect to have alcohol in this sample, and alcohols are very good sacrificial agents. So these are the most likely candidates to show you that we have all the parameters, and then based on the parameters, for example, I will only show you this is a acidic sample, low conductivity, low concentration of harmful inorganic ions, low turbidity, high organic content, and high alcohol content. So you can understand why we consider that this is a promising sample. And the reasons why we have selected those 2 as unlikely candidates, because they have is not relevant alcohol content or organic acids content. And as final remarks, we look at the integration of these wastewaters as source of solar photocatalytic action production is a compelling dual opportunity. We can see that this approach we can use inorganic and organic loads like alcohols, saccharides, and effective sacrificial agents. And these guidelines in this report have identified critical parameters influencing the viability of this method, such as organic content, COD, BOD, pH, dissolved oxygen, turbidity, light scattering compounds, and also the presence of inhibitory inorganic ions. So some studies suggest moderate high concentrations of organic pollutants and can enhance photocatalytic hydrogen production efficiency. So we see that we can have different results. So photocatalytic systems powered by sunlight can be deployed near the source of wastewater generation, reducing transportation and operational costs. This is also important, and also the complexity of the wastewater matrices, variability in composition, and potential for catalyst deactivation underline the need for through characterization, tailored pretreatment, and careful system design. These guidelines provide a step-by-step. These guidelines that we developed provide a step-by-step decision-making framework for assessing the suitability of utilizing these wastewater streams as sacrificial agent in photocatalytic production. And it begins by identifying those parameters that I have highlighted in So at the end, we can say that we have some wastewaters that are classified as likely but subject to pretreatment or testing, or unlikely or unsuitable. And this helps. We had 27 samples, and we come up to 8, then 4, and now we are looking for 2, the most. And well, this is my final message, which is that harnessing the industrial wastewater for photocatalytic production represents a step towards circular economy, and also these when waste streams are transformed into energy vectors, supporting Europe's goals for carbon neutrality and clean energy transition. I didn't show any results regarding the photocatalytic test for the sample. This is the work of the team for LNEG, and we are now in this part of the work. So my thanks to the team of this for the deliverable that worked in this deliverable, and also to the project. And thank you also for it.
Okay, thanks. So at this moment, I would like to ask Adriana Zaleska to join us here. She's a professor at the University of Dansk, expert on the development also of photocatalysts and photoactive materials, and she will now give us a lecture on metal organic frameworks for photocatalysis of CO2. So thank you, Adriana.
So good morning, ladies and gentlemen. Maybe I can sit. It will be maybe more comfortable for this presentation. So in today's talk, I would like to give you more details regarding our work in the field of MOB applications in photocatalysis. But I would like also to give you some general information about this group of materials, and I would like not only highlight, some benefits, and I would like also to highlight the limitation of this group of materials. Back to MOB. So as I mentioned, probably everybody in the world yesterday just started to learn that we have this group of materials, and journalists so-called it, it's super sponge materials. Yes. Something new, name for the MOBs. And 3 scientists, also including Professor Yagi from Berkeley, was awarded. And Professor Yagi, he's generally one of the pioneer of the application of MOBs just to recover the water from the air. Just thinking about, recovery the water from the, maybe also in the desert area, just to store, and he prepared MOBs which could be used in thousands of cycles, absorption and desorption of the water. But generally, MOBs are defined as a highly porous, conductive polymer materials. And what is interesting, I think that they are created by the combination of the metal center coordinated by organic linkers. And if you see for the periodic table, all these metals highlighted in blue could be incorporated into the MOBs, and they could be coordinated with different organic linkers, especially containing carboxylic group. So it makes, millions of possibilities of creating of new materials. And I think that it's, the reason that so many people try to also use the MOBs in the field of photocatalysis. But MOBs also, are reported regarding different unique features. So generally, they have a so well-developed surface area. Some of them have, more than 6,000, and as I remember, the highest surface area reported for MOB was almost 10,000 square meter per gram. So it's, huge if you compare to the activated carbon or another sorption material. They have also so high capacity regarding carbon dioxide, sorption. So people try to use them for the separation of carbon dioxide from the gas stream. And they also, some of them, also show this break effect. So they could change the structure if we use some external, conditions. And some of them shows, photocatalytic properties. And also we can play using different metals and using different linkers. We can play with the FOCO and LUCO position, the optical band, and generally I use this different nomenclature because it's recommended, because they are not typical semiconductors, rather something like organic compounds. So photocatalytic society try also to use to apply this kind of materials in photocatalysis. So what is the unique in the case of the MOFs? So if we try to build this kind of structure, first in the first step, we try to connect the metal center in the form of just metal ion or sometimes metal oxides cluster with the organic linker. So in this step, usually we create so-called secondary building units, and just by connecting the secondary building units in the very hierarchical structure, we are able to create this high materials and control, the morphology of these materials. So generally the geometry of the geometry of the secondary maybe I can try use now this. The geometry of the secondary building units affect the final morphology, but also porosity of these materials. Okay, now it's working. So at the moment, it was, I think, reported more than 1,000 of different synthesized MOFs, more than 500,000 was predicted, I mean, theoretically, that we could coordinate metal with different organic linkers, and much more possibilities still we have, in the case of this kind of material. And the history of application of MOFs into photocatalysis is quite fresh, because the first report was, in 2006. So it was so the MOF was applied for the degradation of some pollutants, and next, people try to use the MOFs or combination with MOF, even with the metal particles or with semiconductors, also in the hydrogen generation and carbon dioxide photoconversion. And the MOFs could be used themselves as a photocatalyst, or in combination with different semiconductors. So in this combination, they could, play the role of the photocatalyst or the matrix for the, semiconductor materials. Sometimes the small particles of semiconductor materials are just distributed at this well-developed, surface area of the MOFs. So I mentioned that we have, more than 100,000 of MOF synthesites, but only a limited number of MOFs could be used in photocatalysis due to their, optical properties, band gap structure, but also due to their stability in the photocatalytic matrix. So usually we use some organic solvents or water or mixture of them. So among them, we decided to use this yesterday mentioned meal 1 to 5, which contain titanium atoms. So titanium is well-known photocatalyst, and also generally MOFs containing the metals which are present in the semiconductor nanoparticles usually also possess some photocatalytic activity if they are enough stable in the reaction environment. So this MOF is built of titanium center and aminoterephthalic acid, which is used as a linker. It could be also, it's possible also to introduce another functional groups, but we would like to use this MOF for carbon dioxide photoconversion. So we decided to use the linker containing amine groups for better coordination of absorption of carbon dioxide. And generally, this kind of linker is relatively cheap if you compare it to the another linkers which are used for the MOF synthesis. So firstly, as I mentioned yesterday, we decided to modify this MOF by introducing of copper and silver in the form of ions or nanoparticles using 3 different methodology or of modification. But when we start to work with this MOF and when we try to apply this MOF for carbon dioxide photoconversion, firstly, we had to fix the problem how to really estimate the efficiency of carbon dioxide photoconversion into the formic acid in the presence of this generally organic semiconducting materials, because we have to be sure that the formic acid is really result of carbon dioxide photoconversion, not result of the conversion of solvent traces or something which is present at the surface of the MOF. So firstly, we concentrated how to purify the MOF and how to prepare the MOF for the checking their photoactivity. So we check a few different methodologies, and finally we decided that for this MOF, but I would like to emphasize that for each MOF you should to find, separate or different methodology for the purification before photocatalytic reaction. So we purified it through the 2 hours irradiation in the electrolyte, but in the presence of bubbling nitrogen, so generally inert gas. After this, we all the time check this MOF if to irradiate this purified MOF still in the absence of carbon dioxide, if we observe formation of our final product. If yes, we have to prolong this purification, step. If not, we can start our photoconversion reaction. And generally, also, if you look for the literature in the field of MOF, usually after synthesis, people activated MOF. So they remove or change the solvent, remove the traces of solvent which was used during the synthesis for the solvents which are easier for evaporation or to remove. So also in our work, usually firstly we activate the MOF, next we purify the MOF, and finally we use them for the photocatalytic purpose. So the procedure is so long. Okay. Once again, I can't, change the slides.
Yes.
Now it's better. Okay.
So I guess maybe sorry, let's try with the other camera.
Yeah, okay.
Yeah, we shouldn't
Yeah,
use
yeah,
this one.
yeah, okay. So just, just to confirm this, I would like to show in this picture, you can see if we use, most without purification, how much, the formic acid could be produced and how, misleading results could we obtain, if we don't use this purification step, and also, the reference test just to compare efficiency of our MOF in photocatalytic reaction. But finally, if we, and here you can use, we try to compare different purification methodology. So for this MOF, as I said, we choose the specific way how to prepare it. And finally, if we after this verification, we can compare, but also we show, all the tests. So in the dark conditions, in the presence of irradiation and inert gas, and finally in the presence of carbon dioxide. But also finally, usually we confirmed that the final product is really a product of the photoconversion using labeled carbon dioxide. And in this work, as I mentioned, we used 3 different methodologies. So we, for modification of the smoke, we produce copper ions into the structure or coordinate these copper ions with the linker in the post-synthetic modification. So firstly, we synthesize the MOFs. Next, we soak it in the solvent, organic solvent, containing the copper. And finally, we confirm that it's really coordinated copper and stable system. So we also introduce the copper during the synthesis, and partly titanium atoms have been replaced by copper. And in the last method, we used photo deposition as a modification method. So both copper and silver generally are present in the oxides, not in the metallic forms. And the method of the or how this the presence or chemical state of this copper and silver species have been generally confirmed using different techniques depending on the methodology of the modification. And what we observed that this method in which we used this post-synthetic metallation using the copper was the most beneficial for the carbon dioxide conversion into the formic acid, and this material have been active under visible light. So I mean that we used the wavelength longer than 420 nanometers. So for the best materials, we use these materials into the 3 cycles, and we observed that generally the level of the final product production is stable. And what was very important for us using XRD, we also confirmed that we still have a MOF after this few cycles of photoreaction, because also some MOFs are not so stable during the irradiation. So for the best samples, so we also do action spectral analysis just to confirm and find what is the apparent quantum efficiency, even in the UV and also visible spectrum. And as I said, we use the okay, so you have you would like to leave, so I couldn't touch anything. So we confirm using the carbon labeled carbon dioxide that and we confirm that we have this isotope labeled carbon in the product. But I would like to emphasize that the yield of this reaction at the moment is, of course, very low. So what is generally the mechanism? Because we use the electrolyte, it's the mixture of 3-ethylamine with the acetyl nitrite. So the hydrogen is generally from this sacrificial agent. Sacrificial agent also increase solubility of carbon dioxide into the reaction mixture. So it also enhances the final yield of the reaction. And if we look also for the band gap structure, we know that it could be excited by visible radiation. So the final product is formed from the hydrogen, from the sacrificial agent and carbon dioxide, which was used in this reaction. We also finally try to estimate what is the effect of the metal content of this copper content, because the application of the copper was more beneficial than application of the silver in this reaction. So we introduced different amount of the copper, but using this synthesis of MOF in which we introduce the metal ions and it replaced the titanium ions in this SAP units, secondary building units. And what we observed that if we increase the amount of the copper, we observe decrease in the VT surface area of the MOF, but and generally we also confirmed using ICP methodology the real amount of the copper which was incorporated, and in most cases it was very close to the theoretical or to the amount which was introduced during the synthesis of the MOF. If you look for the XRD, so we can observe a slight move in the position of the main reflex, which is characteristic for this MOF. So it also means that we introduce, the second metal into the structure of the MOF. And this MOF, this series of MOF was used for both for the hydrogen generation formation. So we found that generally specific amounts, so 1 weight percent of the copper is the most beneficial for the hydrogen generation, and it's it's a huge difference if you compare to the another amount. At the moment we are not sure how to how to understand this. We also observed that if we separate the MOF after synthesis, we still have, the structure of the MOF. So it is very important for us. And generally, the same tendency was observed for the carbon dioxide photoconversion. So the MOF containing exactly the same amount of the copper also shows the highest activity in carbon dioxide conversion into the formic acid. And also for this area, we used, this labeled carbon dioxide to confirm that really we have the conversion product. And finally, we try also to support this experimental work with some DFT calculations. So the theoretical chemists try to simulate how the in how the introducing of these amine groups and also introducing of the copper ions, depending on the amount, affect the band gap structure. So we can observe, you know, the difference of the band gap and also positions in the HOCO and LUCO. And we also could correlate this changing in the band gap structure with the observed increase in photoactivity in our reactions. But finally, I would like to concentrate on the limitations of this group of materials, and we can look for both photocatalyst process and the synthesis of MOFs. If we look for the photocatalyst and, you know, related papers regarding application of the MOFs for especially carbon dioxide photoconversion. So not too much MOFs have appropriate HOCO and LUCO position, and we have to look and find, you know, which MOF have the best, you know, fit different photoreactions, because we have different requirements regarding the oxidation or reduction. Most of them are possess low capacity for the carbon dioxide sorption, and generally we observe that we a little bit can correlate the sorption properties with activity in carbon dioxide photoconversion reaction. And of course, most of the MOFs are not stable, especially in the aqueous solution or under the irradiation, especially UV irradiation. So they are more stable if we use visible irradiation, but not too much MOFs could be excited by UV irradiation. The second problem is just with the process, how we, you know, check photoactivity in our labs. So people use absolutely different media. So it's also, and in some cases they don't report it, or what is, you know, the reference. So how much of this product is just after irradiation of organic solvents, or just after irradiation the MOF of the synthesis. And also there is some limitations regarding the analytical methods which are used for the identification of the product. And finally, of course, the synthesis of the MOF is, I think, one of the great limitations, because most of the synthesis, it's a very long synthesis. If you used solvothermal or generally solvothermal synthesis, the duration of the synthesis usually is, you know, from 24 up to 48 hours. So I think that it's impossible at the moment to think about the application. So the second problem is with the activation of the MOF and purification, even if you would like to use the MOFs for desorption or for the photocatalysis. And the cost of the synthesis at the moment, if you try, you know, to compare the cost of the MOFs which are available at the market at the moment. So I think that the cheapest, even the, you know, the company which proposed the MOFs, they synthesize only the grams of the MOFs, and the cost of the grams is about $100. And if you compare it, you know, with the 1 kilogram of the PM5, so it's a huge difference. So, but the trend regarding the synthesis in the MOFs at the moment is just to use some organic ligands from the biomass, or some organic ligands from which could be obtained from the plastic waste by hydrolysis of the PET, for instance. So maybe it's some, you know, it could be some future for the MOFs, just to decrease the cost of synthesis, and finally to find, you know, the MOFs which also could be suitable for the photocatalysis. And generally, I would like to thank all my groups, and thank you for your attention.
for you. I would like to invite Dr. Peter de la Peña from IMEDEA to present us. And in order to do so, I just need to. Okay, let me just. Okay, you should be able to present now. And so thank you once more for your availability for this presentation.
Maybe when we wait to share the presentation, I can start with my talk and slides. So I'm coming from INDEA Energy. INDEA is the institution. It's a private research institution, but funded by the regional government of Madrid. And we are 7 INDEAs. At the beginning, we was 8 or 9. I don't remember well, but some of them go down. And we are in the energy, but we have also in their materials, in their networks, in their water, in their, I don't know if it's working, okay, very good. So in their neuroscience, in their material power networks, food, neuroscience, water, and energy. So we are located in different areas of Madrid, and sometimes collaborate, sometimes. But this is the main idea. In the energy, well, in the energy is constituted by 8 units, 8 research units, thermochemical process related with mainly catalysis, heterogeneous catalysis, thermocatalysis, electrical system unit that is working on development of software and hardware for grids and electrical management, electrochemical process unit, batteries, supercapacitors, water treatment for unit, photocatalytic process unit. Later I will show you this is our objectives. Biological process unit that is related to microorganisms and microorganisms and biological energy, for example, algae or yeast or biofood production and things. System analysis unit working in SCA, LNEG, EA, other 8. And the high temperature process unit that is working in really high temperature, more than 1000. Now we are trying to combine the collaborative task to decrease a little bit the temperature to 200 or between 100 to 500, 300. And the advanced power material unit that mainly is focused on metal-organic frameworks, but other related materials. So the photocatalytic process unit mainly work trying to use light, direct or indirect way, for example, with PV. And the idea is to convert not only carbon dioxide, here the carbon dioxide, but they try to produce chemicals and fuels with carbon dioxide, hydrogen, with water, nitrogen to produce ammonia for other possibilities. So we are working in multifunctional materials, advanced characterizations, performance, and something new that is the implementation of artificial intelligence tools and validation in different technologies. So the idea is that one of the main problems of this reaction regarding to solar fuels or solar chemicals is that we fight against the thermodynamics. Okay, it's difficult to fight with the thermodynamics, but in this case, it's more difficult to fight with the kinetics. So it's very important to understand all of this reaction in the different time scales that they are producing. So the idea is to develop different tools to understand what happened in the femtosecond, picosecond, nanosecond, microsecond, and the catalytic reaction that is milliseconds time scale. The group is divided in different areas. One of the areas is the synthesis of materials. In this case, we are working with different kind of materials like homogeneous but only small application. Heterogeneous catalysis to catalyst. We are also working in single active sites, hybrid system with different ways to organize the materials, and afterwards in order to try to enhance the production using other in the light spectrum. We are also developing different kind of technologies. We are working in photocatalysis, photovoltaic plus electrolyzer, and photoelectrochemicals. Today we focus on photocatalysis, but in which we have different examples like carbon dioxide reduction, solar hydrogen production, like biomass or other sacrificial agents, nitrogen fixation to produce ammonia, but also urea, photocatalysis for chemicals, and photothermal catalysis for different kind of hydrogenations. We are also very interested in to understand what's happening inside of our materials in reaction condition, because we need to understand what happens when material is working, and we combine different kind of characterization techniques like chemical spectroscopy, electrochemical characterization. We have also reactive in single characterization, such as reaction or near SPS, Raman, another kind of analytical techniques, and theoretical calculations in order to understand what happened of all of these kinds of technologies. Okay, this is the activities in the photoelectrocatalytic team. We are working in different kind of anodes, but mainly visible parallel. We are working in electrocatalytic hydrogen and hydrogen production or oxygen evolution reactions, and also in carbon dioxide reduction or ammonia production. We make metal chalcophenides, and we are working also in smart windows. And now we have a new area that is working in photovoltaics. But focusing in solar fields, this is the yesterday in our database. You can see that I remember that all of these lies mean one point in a database related with titanium dioxide in carbon dioxide. As you can see here, this is a dispersion. This is a dispersion graphic, and as you can see here, the dispersion is around 7 orders of magnitude in the different between the worst result and the best result. So this means that we need, of course, standardize, but also to understand what happened in the materials in order to enhance the production, but also to don't overestimate the production in order to not include noise in the system. So this is when I start to work in carbon dioxide reduction, I try to avoid titanium dioxide. Okay, because a lot of people is working in titanium dioxide, but finally it's not possible because even working in UV light, not the best result, but the combination with titanium dioxide can give us the higher production in the case of carbon dioxide or compared to other materials. But the main problem is that even with this simple catalyst, because it's titanium dioxide, we don't have more complex systems like polymers or metal frameworks or that kind of things. We have titanium and oxygen. We have a lot of uncertainty about how works this material in carbon dioxide reduction. Okay, so we started to characterize our sample in order to determine what happened with the production of different products in this reaction. We started to work with in situ drift in order to understand what happened, which is the peak, how can associate the peaks to some molecules absorbed in the surface of our system. But other problem is that when we revise the literature, we observe that we can find plenty of assignation for each group. So this means that, for example, if I would like to describe what is this products absorbed in the system, and you revise the literature only with titanium dioxide, not with other methods or other catalysts, you can find a huge dispersity of the wavelength ascribed to this product. So this means that you can say everything that you want. If you would like to say that you have more than 10 carbonates, you can say, or you can refer to literature data. If you want to say that you have, I don't know, bicarbonates or bridge bicarbonates, you can also say. So it's very complicated to understand what happened in the reaction, maybe only with one technique. So we need to combine several techniques, try to find some intersectional point in order to know what happened with the mechanism of carbon. Not only the so we combine this in situ drill with the fertile level carbon and air, but in the surface, not with the product, what happened during the reaction, the surface of our material. With the near HCS, both in ALBA and in our installation, because we have a near HCS, for example. But for me, the most important thing is the regular adaptation of the thing. But something that thinks also carbon dioxide water is a little bit more complicated, because when you see the circuit of your system, you don't only have oxygen, titanium, and hydrogen. You have also organic carbon, you have also carbonates and bicarbonates. Okay? So this means that when you put, this is in gas phase. You can also work in liquid phase, but we are more interested in gas phase. When you introduce carbon dioxide and water and you turn on the light, the first thing that occurs is that you are oxidizing the organic compound that you have in the surface. And if you have a partial oxidation of this compound, you can also see some product that we found in our reactions. Okay? In addition, we start to work with catalysts. Something that seems easy to explain. And we have a party of reaction. And this is some of the reactions that could occur in our system. Some products we have rejected with different things. So here I understand the difficulty of the carbon dioxide reaction from other related reaction. Okay? So the only important thing that is try to change selectivity. And thermodynamics is important, but then we know that the kinetics is even more important. So this is a collaboration with Imperial College, with the James Allen Group, in which we introduce silver. And when we introduce silver, we see some changes in the selectivity. We produce less amount of carbon monoxide and higher amount of methane. We perform a lot of characterization because we like that. And we introduce this transient associated spectroscopy. And as you can see here, the time scale between this is the applied to time of photoholes generated in titanium dioxide. So when we have a titanium dioxide, these pairs live 0.5 milliseconds, and when we have silver, this leaves 3 times more than in the case of only titanium dioxide. So this means that silver trap this electron, maintain this electron more time, and then we have more possibilities or more probability to transfer these electrons to the carbon dioxide and then produce methane that need more electrons than carbon monoxide. Okay. But the idea is to move to other kind of materials. In this case, it's like hybrid materials. So we are working with organic and inorganic semiconductor assemblies. So this means the use of organic or semiconductor organic polymer or porous nuclear polymers with an organic semiconductor like hydroxide. We are also working with inorganic frameworks. The article is very interesting, and I would like to focus on the other kind of hybrid materials, organic and inorganic semiconductor assemblies. We develop a different kind of conjugated porous polymer. The more known is linear polymer that is very useful for PV cells because you can play with different flavor pieces, and it's very interesting because they absorb light and then the current, maybe the electron will jump to different levels, but I don't know. It's true. So, but the idea is to work with three-dimensional, two-dimensional conjugated porous polymer. Because the main problem with linear polymers and photocatalysts is that they are very unstable, light and water. So the idea is to work with these three-dimensional structures in order to increase the stability. The main problem is that we increase the stability, but we decrease the conductivity. So sometimes it's difficult to have everything in the light. Box, okay. We have several examples with this kind of CTPs, so conjugated porous polymers, and the advantage is they have high stability, high thermal, more thermal and photostability, like instead of linear polymer, stable in aqueous media, absorb the great for spectrum, they are semiconductors, and so the main advantage they are micrometric particles, pore solubility, pore stability, and not pore but decrease in the electrical component. We define different kinds of strategies to prepare this conjugated porous polymer, like materials, and then I'm going to show you some examples of that. Mainly a reactor. For example, we work with multi and modified system and different alkyl molecules as a structural moieties. So, in addition to most other interesting field or other interesting area of crystalline polymers is called organic frameworks. That it's also proposed by Omar Jaggi, that as you know, is a new Nobel Prize in chemistry. So we developed 2 different GOVs based on body light and we tested in hydrogen production. Okay. This GOV has a mixture with titanium dioxide in order to construct this kind of hybrid material. We optimize the charge of the polymer and we tested different on-off reactions, but also proceeded here up to 30 hours in our reactor. This is not a start or reaction. We start to work with the materials for 5 hours. We take the hybrid system, we filter, we clean and we filter, and we introduce again in our reactor. This is in liquid phase, and we use these materials in hydrogen production, and we maintain the production. This is the example with the WOFI, the comparison modifier. This is important because we estimate is the transfer in these materials, and we see that we increase the chart of the electrical curve leads between methanoic oxide, we use a polymer. We need polymer with methanoic oxide. We see different signals. But we found a linear ratio if we compare the transient and total lifetime our system with the hydrogen production, or less linear 5. Oops. And this is our cost. Okay, so I will try to. We tested these materials also in gas-phase reaction in a real solar reactor that we have in the roof of there. This is our CTC reactor. We can skip the video because everybody knows this reactor. And this is so here. This is the testing in hydrogen production using ethanol. So as a reduction agent, here you can see the core organic patent in our system and the production in 3 days. The people that doesn't work with core organic frameworks maybe doesn't know, but if it's very difficult to produce a metal organic framework, it's more difficult to scale a core organic framework. So this means that we need, I don't know, about 3 or 4 weeks to produce enough code to make the framework in the solar line. Okay, I will explain this part because one of the problems with these materials is that they are exposed. They have surface area, but they are aggregated. So if you want to disperse in a field or other possibility, it's very difficult. So we tested different strategies like emulsion for ultra mini emulsion in order to produce small particles, more 50 nanometers, and we increased. This is the production with this both and modified with the bulk system ultra nano systems. So we increased a lot the production. And when we measure the low line of the curve, you have seen that it's more or less the same that in the whole system. Okay, so this increase is not due to the kinetics, but it's due to the enhance of the dispersion of these organic frameworks in the catalyst. Okay? So this is the try. Okay. This is some examples about the materials and process and technologies that we are developing. And I will try to give you my vision for the next year. We are working on that. As you can see here, this is the traditional approach in solar field production, and our idea is to include artificial intelligence and automation in order to enhance this growth in the solar field production. So we are developing this kind of cells. This is a electrochemical or photoelectrochemical upper window size of these cells. And the idea is to use several of these cells in order to produce a lot of experiments at the same time. But not only high-throughput synthesis, but also to include just big lab in which you can maximize the synthesis of the material and the reaction of the materials, and also the idea that in this statistical testing, we are developing algorithms, we are developing tools for analysis and estimating, and the idea is to scale up the processes, but to work in collaboration with other labs, even spending our parents, working all of us with the same level, and then with the lot of experience and use the same data in order to understand. So I will skip this part. This is the interface that we are developing, materials with analysis of the system and things. And this summarize this. I don't know if it's possible to click or not.
It's okay.
So, oops, maybe I this is the so this is the idea. No. And that's all. We also join in the lab with us, other things that.
Thank you very much, Victor, for your really nice presentation. We will now move to the next presentation. And so I would like to invite here to the podium the Sarah Meitz from Intec in Austria. That's you can use this one if you want. Okay. So thank you very much, Sarah, and please go ahead.
Yeah, good. So I will take the next 15 minutes, 20 minutes.
20 minutes.
20
Yeah.
minutes. For like showing you also some progress we did like we said on solar reactor design. So actually we did a lot of work in the project now on hydrogen production, but I will also give you some other things that we are at the moment working on. So
I did test this beforehand.
Only works natural.
Not even with maybe now. Yeah.
Good. I think in general there is like a consensus on the topic that we need for climate neutrality also sustainable pathways for the production of fuels and chemicals. So I think that's a general thing. And for this, on the one hand, abundant molecules are important and waste that we depend on. So for example, CO2, N2, but also water. And in terms of waste, also wastewater. And on the other hand, we also need like energy that should be also in the best way abundant, and here solar energy comes into play, and also solar to X technologies, because they are available to convert solar energy into chemical bonds, on the one hand on a direct way, but on the other hand also an indirect way. So an indirect way means mainly via electrochemical energy, so electrochemical processes. So it means that, for example, via water electrolysis to produce hydrogen. But of course, these technologies really depend on electricity, and the best way is provided via green electricity, so PV. But also here we come to a point where we have limits in electricity production, and therefore I think in terms of having a good technology mix, it's important to also go the direct route more or less to this chemical energy and really use solar energy directly to create chemical energy. And this is actually where photochemical and also photoelectrochemical processes come into play. In general, as the topic is also a bit on showing you results on hydrogen production, I would like to also take up a bit the topic we had yesterday on the different values that are out there, or the different metrics and KPIs that are out there, and also go a bit into the topic of hydrogen production and show you just some examples on efficiencies from hydrogen production, because actually in general, when we look into literature for photocatalytic, but also photoelectrochemical systems, we know that there are photoreactors available in different designs, different geometries, different scales, but actually still at the low tier L level and at low efficiency. And when we now look into, especially for hydrogen production, into the solar to hydrogen ratios, we see that for the different processes, there's a big variety of efficiencies available. So for photoelectrochemical systems, we find a lot in the range of 3 to 4% of solar to hydrogen, but also find maximums at 19%. When we go to photocatalytic processes, we see like ranges from 1 to 3%, but also show some values of higher than 6%. But in the end, if you would like to really now compare different results, we come exactly to the problem that we focused yesterday at the task meeting, that the results cannot be compared at all. And the other problem is that we have, when we now talk about really the direct use of photons for chemical energy, that at some point we might need to go the step towards the real sunlight applications. And then we face the problem that the experiments are often performed in small lab scales, but also just at defined wavelengths. So we really have a problem to then go out to real applications, to real sunlight, and really show the efficiency of the different processes. So it's really about the challenges that we need to also like find the route or try to adapt all the processes towards the real sunlight application, that we also have the catalysts available that can work in real sunlight or in visible sunlight. But of course, also on the other hand, I'm trying to find a good combination in like catalyst development with the reactor designs, because actually also the reactors itself face still problems in energy and mass transfer and also in the scalability. So there's also this need of a good collaboration between the topics somehow. And actually, this is also the point where we, at the work that we are doing at the Institute, try to take up these topics in different approaches. So on the one hand, of course, in the Task 72, we heard a lot about it yesterday, but also today, with what we would like to do in terms of metrics and key performance indicators and try to find out about ways for standardization. But another topic is really also this utilization of a broader spectrum of the solar light. And I think with the project Spectrum, like we heard today, this is already maybe a possibility to find a way of trying to make it possible of also photo processes, even if there are low efficiencies at the moment, to really make them economically in an overall concept at an early stage, and then have possibilities to further advance and increase efficiencies. And this is also something that we take up a lot in our research work, and also product collectors, for example. But on the other hand, we also go a lot into like novel photoreactor design, because we're doing a lot of process engineering, and they are trying to take up strategies and trying to find out of how to combine it now in the best way with solar photoreactors. And here, two example applications we are working at the moment on is really this hydrogen production from wastewater. We have had here this national project Photoreactor, but also now expanding towards these multi-product collectors to go on in this direction also, and based upon these results. And in parallel, we're also now working on CO2 reduction, and here also in an EU project, the project Desires. I would like to start now to show you a bit on the work we did in the project Solar Reactor. So the objective was really to develop an efficient solar photoreactor design and do a proof of concept also in real sunlight applications. So in the whole development step, we really started on the first step together with the Technical University of Vienna. So Rokan is here with us on the catalyst development. So actually, we tried to find out how we could work in wastewater for hydrogen production and find a good candidate, and we ended up with bismuth vanadate in this case, to really make the switch in the first step from mainly UV usage in catalysts to also its visible light ranges, and here also making the switch in terms of the scale up. So we started off with really small electrodes, but also tried in the project already to do a first scale so that we can try to find out, does it work and how could it work. Then the second step was really to develop a solar reactor design and integrate these upscaled electrodes and test them in real sunlight application for hydrogen production in different wastewater treatments. And for this, we also constructed a small one as indoor experiments, but also outdoor experiments. So here just a quick glance at what has been done in the synthesis of bismuth vanadate. So as already said, we have here the TU Vienna with us, and they were actually responsible for synthesizing the bismuth vanadate. In the workflow itself, it was like this, that we started off like with this first type of the bismuth vanadate electrodes, and they were pre-characterized at the TU Vienna. And then they scaled them up, and we ended up with a length of around 15 centimeters of electrodes for the first usage in the solar reactors for real sunlight applications. In general, we then in parallel, as already said, try to find out what could be now a good solar photoreactor design. So we heard now about all the drawbacks and the limitations we have somehow. And actually, we were at the point where we said, okay, now we have catalysts available. They, for in this case, plated, but also maybe for other applications in the photocatalysis, immobilized or as powders. And on the other hand, we have the electrolyte. In this case, it was wastewater. But we still had the problem with the limitation of the state-of-the-art of solar photoreactors. So we had low efficiencies. We knew that there is often the insufficient supply of the catalyst surface with the reactants, and also the problem with the delayed removal of products. So maybe products accumulate, and then you also have drawbacks in the whole efficiency of the system. And at this point, we came across the idea that there might be a possibility to, in general, introduce here a novel flow reactor design, oscillatory flow reactor, where we had a lot of experiences with in other processes, and try to combine now really all the basics of photocatalytic and photoelectrocatalytic processes with oscillatory flow reactors. And this, in the end, made our oscillatory flow solar photoreactor that we designed within the process. Actually, it's like this, that in general, that we introduce oscillatory flow behavior on the fluid, so the electrolyte itself inside the reactor, and via this create turbulences. So we have really the possibility to have a good mixing inside the reactor, but at the same time, we decouple the net flow going through the reactor from it. So we also can manage, for example, high residence time inside the reactor, but still manage to have a good mixing and turbulences inside the reactor. And via this, increase the energy and reduce the diffusion losses, but also enhance the product and reactants transport inside the reactor. Here are some pictures on how the reactor was designed, actually. So we ended up with a reactor geometry in a tubular system, and having the tubular system quite flexible. So actually, we are now have the possibility to easily switch between photocatalysis and also photoelectrocatalysis for the tubes that we have by just different setup of the tubings itself. But we also have possibilities for size variation. So the single tubes that you can see here above are more that can be used at once, but also the single stack in extra cells. And we have the possibility to also connect them in multi-tube applications. So in a serial, but also parallel way, and also in different compartments, so also in two-compartment system, for example. A specific part that we have with the reactors are these bubbles. So like you can see here, this helix inside, and that's actually an important part we need in these oscillatory flow reactors, because they more or less introduce also these turbulences and the oscillatory flow. In this case, we stick with a helix for the system, but we also tested perforated plates, and they are especially, for example, in two-phase system, quite interesting when you work with liquid and introduce gases inside the system, that they also have here a good mixing and homogeneous mixing inside the system. And in this case, we also worked in the first version of concentrating mirror. This is a short insight into the test stand, how it looks like. So actually, we worked a lot with our outdoor test stand. We have here now a suspended platform that we put out of our south-facing lab window, and where we are also quite flexible with our tilted platform, where we can also vary the angle of the platform that we have. In parallel, we also have an indoor test stand available for artificial light source experiments that mimics more or less the band gap from 370 to 470 nanometers of field exposure. What we can also do with the test stand is to have like
good real sunlight measurements. So actually we have a weather station on the rooftop of our institute, and we measure in parallel also spots on the reactor in terms of irradiance, and we can correlate more or less the results from the weather station that is really taking measurements in minutes there, and correlate with the angle we have on the reactor and also the measurements we have on the reactor itself. Yeah, with this setup, we went into experiments on the one hand in artificial illumination, and here the interest we had on the oscillatory reactor, because in this project we actually applied this for the first time. I wanted to see of how now the oscillation really affects the yields of products we would like to reach, but also looked at different wastewater and how the wastewater influenced the hydrogen production. And with these results, we went into real sunlight experiment and also again rechecked this validation of oscillatory flow in real sunlight, and then tested in different sunlight conditions. So here are results from artificial illumination. So like I already said, we did experiments to see the influence of oscillatory flow, and actually parameters that we could define are the frequencies and the amplitude of the oscillation. So more or less how big the hub is that we oscillate and how quick we oscillate. And here we could find out that actually an oscillation of around 250 in Reynolds number is or gave the best results in terms of product yield. What we also could find out is that actually when you go too high in turbulences, then this already has a negative effect of the hydrogen output. So at some point you also need to see to find out this drawback between which turbulence is the best, and actually this for us was at the Reynolds number at 250. And here we could increase the yield of hydrogen production of around 20% in comparison to a system without oscillation. We also tried different wastewater components. Actually, we did here some pre-tests already at the Technical University of Vienna. So they pre-tested different wastewater, the combination of wastewater components, and then the best candidates we tried to transfer then into our experiments to go further on. And what we have chosen then was on the one hand EDTA, which is a candidate from the pulp and paper industry. So here maybe also the topic that we also started off with this literature research of which components could be quite interesting. And what we then also started off with was really the point where we said, okay, maybe really these hard to degradable compounds are the ones that would be of high interest also for industry. And that's why we actually took out EDTA for pulp and paper industry. And we also chose glucose from food industry. And we varied the concentrations from 10 to 1,000 milligrams per liter. And you can also see the results on the left side. You can see the different hydrogen yields we produce depending on the concentration. Actually, we see EDTA has much higher influence on the hydrogen yield, also when we increase concentration. Also, glucose gave us a higher yield in hydrogen in comparison to a system without any sacrificial agents, but the influence of the different concentrations wasn't that high as in the case of EDTA. But what we need to mention is in case of EDTA, on the right side, what you can see is again the hydrogen yield over time with the different concentrations. And actually what we have seen there is that especially in the EDTA with the 1,000 milligrams per liter, that we could see this decrease of hydrogen production over time. And that was also on the one hand that we really here had an issue on the one hand with maybe the potential of the electrode, but also a pH change. So over the time we could see that we had a pH change in the system itself, And therefore, we also expect here any intermediates to be produced that could also have an effect on the process itself, but also degradation of the electrodes that we have seen here. And with the results from the artificial light, we went into the standard application, and we did again these different oscillatory parameters. And again, here we came out that we had the optimum at around a Reynolds number of 250. What was also quite interesting, we also then analyzed different amplitudes and frequencies to see just what makes the bigger effect. And actually, it's like this, that the most effect on the hydrogen yield shows the frequency. So by just adapting the frequency, you can have a bigger influence on the hydrogen yield. But actually, the lowest frequency showed us the best results, which is also in terms of maybe later on energy demand that at least it's needed for the oscillation, a quite positive outcome, because the lowest frequencies would also need the lowest energy demand. So that's also quite positive. Yeah, what we did in real sunlight was also a correlation between hydrogen yield and the irradiated power we had on the area. And actually, the system came out with a quite good correlation. So we had a linear correlation of the irradiated power that we had with the hydrogen yield. So the higher the power, also the higher the hydrogen yield was. And actually, the system was also quite sensitive in the end, which was also quite nice, because any small clouds passing by was already detected in the hydrogen yield. So this correlation was really quite nice in the end to give a good result. Yeah, we plotted everything also over time, just to see again on how the results occur. These are results again from EDTA. That's why you also see the decrease in some values here. But in the end, we were at a hydrogen ratio of around 2%, and hydrogen yield between 0.2 and 0.4 grams per square meter an hour. Yeah, and based on this, I already would like to come into the outlook. So actually what we have now gained was a lot of experience in the hydrogen production, but I think here also some improvements still to be done. We gained a lot of knowledge also on the influences of the oscillatory flow solar reactor and what we could improve. And with this, actually, we went into the European project Desired, which is now based on CO2 reduction. So what we worked on now was the transfer of the hydrogen process model to a CO2 reduction process and how we can integrate it into the reactor. We came now out with already an upscaled version of the reactor itself. And what we also did, because the concentrating system and how the mirror looked like wasn't really a target in the hydrogen project, but it is in this case. So in the project Desired, a special focus is also on ray tracing and also create a radiation digital twin. And there design a novel mirror, and that's actually the status that we have. So we now have an optimum design of the mirror, and we integrate the reactor, and in the next months we now go into testing, and also throughout the next year there will be some intensive testing now of the combined system of the reactor plus the mirror system. Yeah, with this, I would like to thank you for your attention, and I'm happy to answer questions.
For your presentation, and I would invite Michael Fullencourt from the German Aerospace Center to join us also here on the floor.
My presentation is entitled Testing of Photoreactors under Practical Conditions using ELR for testability. And here is maybe write something. You can see an outline of my presentation. First, I will talk very briefly about DLR as a general, and what the Institute of Solar future fuels, which will work in, then about DLR's solar test facilities. Then we come to the core of my presentation, testing of photoreactors out of lab scale. So this means under practical conditions. There are some examples I brought today with me, covering a whole range here from photoelectrochemical, photovoltaic, tandem devices, photocatalytic ones, photothermal ones, and also a reactor working with osmotic catalyst and yeah, here you can see some figures about the DLR, the German Aerospace Center, Europe's largest research center for aeronautics and space. And besides these two, we have the research field energy and transport, as well as cross-cutting activities in the fields of security and digitalization, platform technologies and system modeling. And yeah, for us, it's very important to have a close cooperation between science, research, business, and industry. Yeah. Here's some numbers from 2023. All we have 54 institutes and facilities at 30 locations all around, distributed in all Germany. We have 4 foreign offices, more than 11,000 employees, and a budget of more than 1.6 billion euros. Yeah, one of these 54 institutes is the Institute of Future Fuels, and we deal predominantly with the development of alternative fuels, technology development for the efficient and economical production of energy carriers, and also chemicals for a global renewable energy economy. We cover here diverse aspects, solar chemical process development, material and component design, demonstration of these solar processes, and also techno-economic and socio-economic process evaluation. We have 130 employees besides Jülich, where I work, Cologne and Cologne. Yeah, one important thing here is, of course, that we run different infrastructure and large-scale facilities for process development. And here I brought this picture with me. Facilities providing concentrated, natural, or artificial sunlight, starting with LED light sources, the Sokratos facility, high flux solar simulator, solar furnace, the sunlight, which is the largest artificial sun on Earth, and the solar towers, which cover the whole range from laboratory scale up to industrial scale. And for my presentation now, I will show you some examples using these 3 solar test facilities: the Sokratos, the high flux solar simulator, and the solar furnace. Yeah, well, and overall, all of these test beds here are used to test and qualify system and components and to demonstrate photon-driven and solar processes. The Sokratos facility stands for solar concentrator with a rectangular flat focus, has 22 planar facets focusing light towards a focal plane with the dimensions of 2.5 meters in length and 18 centimeters in width. And of these 18 centimeters, 10 centimeters provide really a flat irradiation profile with very low difference in irradiation. We can achieve irradiation levels up to 16 kilowatts per square meter with this facility, and power on the target, if you really use all power captured by the focal area of 6.4 kilowatts. Solar simulator, which you can see in the center, features 10 xenon arc lamps which can be individually adjusted to meet certain irradiation conditions. And the typical irradiated area would here be in the range of several 10 centimeters square size dimension. However, this is adjustable according to the requirements of these reactors. And also regarding the size, very similar would be the solar furnace. The concentrator here consists of 159 assets focusing lights towards the focal area. In terms of irradiation level, both facilities, so the high flux solar simulator and also the solar furnace, are quite similar with peak fluxes if really required. You can easily burn things with these kind of magnitudes here of above 4 megawatt per square meter, and both facilities deliver power on the target up to more than 20 kilowatts. I will now show you some examples of photoreactor testing using the Zokatos facility. Here, one example was I can show you is from the project demo, where hybrid photoelectrochemical photovoltaic device was developed for solar driven water splitting. The final prototype you can see here. All in all, the size was 200 square centimeters, and this is here mounted in the focal plane of the Zokatos. We considered here different photoanodes, so the yellowish surfaces. This was the photoanode capturing part of the light, and behind there was a PV cell mounted, which provided a bias voltage for the water splitting reactions. We have different types of photoanodes, hematite and also bismuth vanadate. And the example I brought here with me is was achieved with the hematite photoanode. And you can see here very nicely that the current vacancy achieved not linearly increase with the solar input. So we were we are able to recover part of the assets. We really allow a large range of irradiance here, and you can see these kind of saturation effects. Clearly showing that there are some kind of loss mechanisms relevant at larger scale, which you predominantly won't detect in very small devices. Another project we already heard about, it's simultaneous hydrogen production and wastewater treatment. So several years ago we looked at this. We developed a chemical tandem device featuring two photoelectrodes, a photoanode and a photocathode. Final demonstrated, you can see in the upper right region with a perforated photocathode at the top, and at the bottom behind the photoanode. But what I want to show you right now here is some results we gained with photocatalytic reference experiments using this two-chamber suspension reactor. It's a flow reactor and allows doing experiments with two different systems at once, directly receiving the same identical light input. This reactor was also mounted in the focal plane of the Zokatos, where also, besides CNI measurements, measure the spectral irradiance really available at the, let's say, window of the laser. Here's one example for catalyst. I said we can measure the spectral irradiance, and what you can see here in this diagram in the course of a day is the spectral irradiance in different wavelength regions, and in red, the molar hydrogen flow, all values relative to the mean of this particular day. And you can see, as you could expect, that the hydrogen evolution quite nicely follows the UV irradiance, what can be expected because of the type of the photocatalyst. Also worth mentioning here, this diagram really nicely shows also that the solar spectrum is not constant. So you have at noon, you have clearly different conditions with a higher blue fraction than in the morning and in the evening. This is also something one might forget to consider. It's really later on. We have to consider the whole day, the whole year of operation, not only one particular operation point at 1.5 at AM 1.5. This is just a team project which is now active and considers photon-driven CO production. We have just started the installation of the whole system. Again, with a reactor hosting plasmonic catalyst to drive the reverse water gas shift reaction. And a special feature here is that we won't use only a natural concentrated sunlight, but also LED sunlight to compensate remaining solar input, or also even allow 24/7 operation. And we designed here some additional optics to homogenize the input into the catalyst domain inside the reactor. It's just a teaser. You will see some results maybe next time. We now come to the iFlux solar simulator. One project that has recently been completed is the Flow Photochem project, which stands for heterogeneous photo electrocatalysis flow using concentrated light, modular integrated designs for the production of useful chemicals. And within this project, 3 different types of modular flow reactors were considered. Photoelectrochemical modules, photocatalytic or rather photothermal modules, and electrocatalytic modules, which were arranged in a demonstrator to finally produce useful chemicals such as ethylene from solar energy and carbon dioxide. And what I want to talk about now briefly is testing of the photothermal reactor, which is the center reactor, where hydrogen and carbon dioxide react via the reverse modular shift reaction of carbon monoxide with the unwanted side reaction of methane production. This reactor had an aperture of 12 centimeter side length and a core area with a side length of 10 centimeters. We deal here with heterogeneous photothermal catalysis using a ruthenium oxide on strontium titanate catalyst deposited on or in a porous Lesford support, and the reactor here features a flow-through design. So the whole flow through the catalyst domain. This reactor was operated at 40 to 80 suns, which is equivalent to a solar power of 1.2 kilowatt. And up front, we made sure that the irradiation flux of the catalyst is reasonably homogeneous by introducing secondary optics, by positioning the lamps, by tuning the lamp currents, and so on. And the right side picture, you can see that the inner area is irradiated quite homogeneously as the reactor requires. And we did 2 campaigns with this reactor. The first one, only the reactor was tested, and the second campaign, the whole integrated system was was tested. Here you can see the experimental setup as it was erected in the high flux solar simulator, with the optics in the center of the picture, where you can see the bright scattering window which we use to provide the reactor, which is located right behind these radiation protection plates with a homogeneous flux distribution. Yeah, the reactor you can see on the left-hand side how it's integrated into the system. Yeah, here are some exemplary results for 500 milligrams of this catalyst for this glass greater than 1 millimeter a day. We can see that we increase the nominal flux of the catalyst flow area, in this case from 40 to 70 kilowatt per square meters. The temperature inside the reactor, referring to the upper blue curve, increases and reaches a maximum value of 650 degrees C, while the reactants in light blue and in green gradually decrease, and the desired product in orange, carbon monoxide, gradually increases. Yeah, don't want to go too much into detail into this diagram, just show that we considered many different parameter variations in terms of nominal flux, total flow, and composition. These experimental data gives a basis for model-informed design improvements for increased solar-to-chemical efficiency. Last but not least, the solar furnace, again providing natural concentrated sunlight. Here I want to talk about the spotlight projects, which uses plasmonic nanocatalyst to tailor for both either Sabatier reaction to form methane or carbon monoxide via the reverse photogas shift reaction. And again, here a demonstration was done in hybrid mode, not only with the concentrated, but also with LED light. Yeah, the solar furnace captures the light, the sunlight, with this heliostat. It's directed towards the spherical facets I've talked about, and they concentrate the light into the solar furnace. And there, this flux guide was positioned, which receives the incoming light and guides and shapes the flux in a way that at the outlet of the flux guide, get nicely homogeneous light again to operate the reactor. You can see here on the right side this arrangement with mirrors at the back, then shutters, an LED system which is included, the flux guide, and the transparent flow reactor. And the bottom pictures here show nicely that the incoming Gaussian characteristics of the light are transferred into very homogeneous flux distribution to make sure that there are, for example, no hotspots in the reactor. To control the input, of course, LED light can be quite easily controlled with control signals, and the incoming solar light you can control by the means of diverse shutters, which open only part of the total pathway of the concentrated solar light towards the reactor. Here are some very brief results, only just in general that the demonstration was successful for both the Sabatier and the reverse photogas shift reaction, and continuous operation in hybrid mode was conducted, achieving 72 hours for the Sabatier reaction and 168 hours for the reverse photogas shift reaction. Good report that the candidates were quite selected. On the right side, you can see some examples of methane and carbon monoxide evolution as a function of the applied flux. The evaluation is ongoing. You will also see here some more results, presumably next time. If you want to have a look at the experimental setup, I can point out here that there is a virtual tour available for this setup here. Okay, this brings me to my summary. So, as you have seen, DLR operates a wide range of versatile solar facilities, which facilitate testing of photoreactors and demonstration of photon-driven systems under practical conditions, going beyond lab scale. We take care of photon management to meet the irradiation conditions required by the photoreactor. And this brings us to experimental data for model validation and requirements as a basis for in-depth understanding and enhancement of processes, systems, components for the production of solar fuels and sustainable chemicals. Okay, that's all from my side. Thanks for your attention. Thank you.